Attendees, Keynotes will begin shortly. A reminder to please silence all mobile devices and take your seats. Thank you. These keynotes will begin momentarily. Please take your seats. Please welcome back Todd Moore.
All right. Good afternoon. Well, welcome back to our afternoon keynotes. I hope you all had enjoyable sessions, informative sessions here this morning. Maybe some great conversations with your fellow attendees, as well as maybe made a new friend as part of lunch. Sit down, enjoy some time with folks, and we have another opportunity for that again tonight at the reception. We have some great keynote sessions here again for the afternoon, so I'd like to get started. Our first session is actually going to be virtual. Sharon Zhao is the co-founder and CEO of Lamini. It's an LLM startup based on Sharon's PhD thesis. Today, Sharon's going to talk about teaching LLMs new knowledge. So please welcome Sharon Zhao. So thank you.
Hi, really happy to be presenting here and talking with all of you. I'm Sharon. I'm the co-founder and CEO of Lamini. I come from both a product background and an academic background in generative AI, with a PhD in it from Stanford, faculty there for a little bit at Stanford in generative models. And I also teach about 250,000 students and professionals online in generative AI. So I'm pretty much obsessed with the space and love it. And so would love to share a little bit more about what I've been building, and also see if there's anything I can share with you that could be helpful as you work with specifically open source LLMs at scale in production workloads. So I'm going to just share my screen. Great. So at Lamini, the overall thing we're doing is customizable superintelligence. Really, the goal is for you to own these models. They're open source models for you to work with. And we're just the infrastructure to make it possible and easy to run. My background, you just heard about, and my co-founder's background, he was one of the original CUDA architects back at NVIDIA, back when this was all starting. He invented LLM scaling laws, along with folks at now at Anthropic, et cetera. He invented tensor cores and deployed large language models to over 1 billion users at scale at Baidu. And so, yeah, this is where we are. If really all you are here for is to hear whether we have some compute for you, well, it turns out we actually do. So if you're interested in compute, we actually are scaling some more up right now as I speak, actually. So by the time you hear this, we'll have a lot more compute available, hundreds more available for you to get on to run your LLM. So now let's see exactly what can you run on these LLMs. Okay, so first, here's really basic call to the Llama model. This is actually a lower level thing where you can actually guarantee JSON calls. So you can just instantiate an LLM here with Lamini and then call, give it, how old are you? And say, hey, here's the output type I want. And I want this guaranteed JSON call. So an int of an age and units string. So the expected output here would be 25 in years. And this makes it very easy to work programmatically, with these models. As you know, that parsing strings can be quite hellish. Another thing that we focus on here is how do we get the model to learn from millions of data points, right? So like you're collecting data from your users and you're gaining more and more knowledge that you as a person, if you were on the receiving side of that, would actually learn a lot more from. So same with models. So how do you make the model actually much more able to accept that data? And that's what we're working on here at Nomini. So both to gain knowledge from that new domain where you're actually getting that information from, correcting old incorrect information. So if there's, incorrect things or things, where you don't want the model to really remember all it's learned from Reddit as the data set or 4chan as a data set, then here's the chance for you to do that by training the model to do otherwise. Behavior change is another very common way to teach the model from data. And so this is all done through commonly known as fine tuning, also just pre-training and training the model more broadly. And training has been one of the most important things for creating differentiated LLMs. So OpenAI did that early on with ChatGPT and GitHub Copilot from their base models, but of course you can too. Nomini is, again, this LLM stack for open models. Here are some stats on what we're doing today. And it's just wrought from 2 decades of best practices that we've learned from building these things at scale. And finally, I just want to note that, to make LLMs successful, you don't just need fine tuning or just training. It's actually doing prompting, RAG, and fine tuning, all of it. And actually, the list keeps going in terms of what you need to do: domain adaptation, pre-training of the models. And so what I really, really encourage is folks to think of this more as an and operation and actually employ all of these techniques to successfully build an LLM. And finally, if you're interested in that last step, which is a little bit more difficult, fine-tuning large language models, feel free to take my course that I teach with Andrew Ng online at Coursera. Yeah, that's it. I'm very happy to be here. Thank you so much for having me.
All right, thank you, Sharon Zhao. So our next speaker is Victor Dabia. He's a principal research software engineer at Microsoft Research. Victor's research is actually focused on Gen AI within the Human AI Experiences team at Microsoft Research. Victor is here today to discuss Gen AI applications via multi-agent conversation. So please, Victor.
Hi, everyone. My name is Victor, and today I'm really excited to talk to this group. Especially, I'd like to talk about AutoGen, which is a framework for building multi-agent AI applications. Importantly, AutoGen is a work of contributors across multiple institutions, including Microsoft Research, where I work as a software engineer. To begin, I'd like to paint a picture. And so in this picture, paint a picture of a future where AI agents help us with increasingly complex tasks. And so, for example, we might ask an agent to write a novel, come up with some sophisticated plan, or help with some supply chain problem. Interestingly, we will probably just give the LLM or the agent a high-level task description, and then the agent figures out how to accomplish the task. In addition, over time, we expect these agents to learn, adapt, become aware of our context, and better help us with tasks. In this future, agents become the new frontier for computing, transforming how we interact with the digital world. But how might this complex task be sort of implemented in practice? And so if we take the last example there, is it possible for Roastery 1 to be exclusively used by Cafe 2? How would that affect overall cost? A few things need to happen. So first of all, we need some sort of plan. And so in this case, we might try to understand the current setup. We might gather some data, clarify assumptions, and then run some financial analysis. Importantly, we also need to act. So for example, we might need to read or summarize documentation, search some databases, consult with some human experts or subject matter experts, and then run some computation. And after all of that, we need to orchestrate communication across each of these steps and then get the final report. And so a few things are sort of important here. An agent that can help us with these tasks must be able to reason. So first of all, plan, sort of deduce next steps. They must be able to act. So for example, they must be able to use external tools, query databases. And then finally, they must be able to communicate. And so this might be communicating with other agents or communicating with humans to sort of get feedback. But Is a single agent sufficient for this sort of complex tasks? And the core argument here is that as we sort of try to address more complex tasks, we might need to shift from just LLMs up down to, let's say, groups of LLMs. And so the current paradigm is that we can apply LLMs to reason and solve tasks. However, we're all familiar with the fact that LLMs tend to hallucinate, or they might struggle with tasks that require multi-step reasoning. To address that, we might give this LLM access to some sort of memory or external knowledge to reduce hallucination, or we might give it access to a computer, a calculator, to sort of help it sort of address complex tasks, like, let's say, computation. Importantly, we will notice that as we address more complex tasks, this task might require multiple back and forths, require complex, lengthy instructions, and at that point, a single agent might start to struggle. And then finally, the current thinking is that we can start to assemble groups of agents. And the idea is that if we have this sort of multi-agent approach, we have separation of concerns where each agent can address a specific goal, leading to improved results. Some prior recent research shows that like a multi-agent setup can help with divergent thinking, improve factuality and reasoning, and also provide validation. And so in some cases, some agents sort of address the task, and some additional agents sort of verify the task was addressed correctly. Okay, so in practice, in theory, the promise of multi-agent implementation is very interesting, is very promising, but the implementation is hard. So how do we specify agents? How do we give them access to tools and LLMs? How do we orchestrate communication between agents and humans and get them to work together as a group to solve a task? And then how do we sort of make all of the participants in this loop aware of each action? And AutoGen was designed to sort of solve this problem. So there are three high-level properties of AutoGen. So first of all, we have a conversational paradigm. So we sort of believe that the primary way to sort of orchestrate sharing of state among all of these agents is to sort of maintain a shared message history and message lists as represented as a chat. And in addition, we want to offer a flexible API that's easy to use, enables communication across multiple agents and humans within the loop, and then make this workflow or API really customizable that we can support simple workflows and then complex workflows. And then finally, we aim to have like a vibrant, growing ecosystem of integrations, and I'll show some examples in a little while. In terms of API, each agent has a simple interface. It can send messages, which is essentially putting in a message into a shared message list. It can receive messages, and then it has an API to sort of act or reply based on the messages it receives. Next, we have three built-in agents. One called the user proxy agent typically will act on behalf of the user and can use tools like, let's say, a compiler. We can also have an assistant agent that has an LLM configured to try to solve problems by writing Python code. And then finally, a group chat manager that can orchestrate groups of agents to solve our problems. The API is fairly simple, and so on the left, how might we sort of set up a two-agent setup? On the left, we have just a simple line of code where we set up a user proxy agent and then an assistant agent, and we just initiate a chat between both of them. In this case, we ask them to plot a chart to show stock price. And what ends up happening is that the user proxy says, here's what the user asked for. The assistant agents write some code. The user proxy executes that code. Some error occurs. The assistant deduces that, okay, some error has occurred. Here's some additional code to fix that, which is to install some dependency. The plot gets generated. Some corrections are made, and then the final output is given to the user. So that was a simple setup, but we can orchestrate these agents into much more complex setups. And so one of the interesting examples is the example A4, where we could have a group setup where some agents write code, and additional agents might work as some sort of safeguard and sort of critique or ensure that like the code that has been written adheres to some security constraints. Finally, I'd like to talk about the set of integrations that we're sort of seeing with the AutoGen ecosystem. So for example, we have support for multimodal agents. And so you can imagine a setup where one agent writes code to generate visualizations, and another agent could be a visualization critic that takes the chart that has been generated, sort of looks at the visual quality of those charts, looks for overplotting, combined axis, gives feedback, and then both of them collaborate to get even much better outcomes for the user. We have examples of teachable agents that continuously learn facts, preferences, and skills from user feedback, saving them and using them in other related tasks. And finally, we're even looking at examples, low-code interfaces that allow users to, for example, declaratively specify an agent. And so in this case, specify the maximum number of turns, the models that are used, and then run tasks against this declaratively specified agent, and then look at the output. So in this case, we have 4 messages exchanged by the agent, and then they can generate a chart that can be reviewed. We can also give these agents access to skills, for example, ability to use APIs, generate images, and then we can even tell them to do things like go ahead and generate a whole entire book, and the agents will sort of interact. In this case, 12 messages, took about 3 minutes. So we asked the agents to generate a children's book, and so essentially use the image generation API and generated an entire book. And so these are some example experiences that we are starting to see users and our team sort of prototype using a framework like AutoGen. AutoGen sort of started out in March this year. We open sourced it in October this year, and in the last 2 months, we've seen quite a bit of growth. We've seen about 18,000 stars on GitHub, about 150 active contributors, 11,000 members on GitHub, on Discord. And frankly, in my opinion, we're just getting started. There are a lot of open problems that sort of are yet to be addressed. So for example, how do we improve communication efficiency across agents? How do we integrate multiple models and optimize for cost? How do we streamline more complex, long-running workflows? And so we hope that you'll join us. AutoGen is an open source project, MIT licensed. Like I mentioned, it's growing, and we're just getting started, and we'll definitely benefit from your help and your contributions. Thank you.
Thank you, Victor. Thank you, Victor. All right. So our next speaker is Charles Srisuwananukorn. Charles is a founding vice president of engineering at Together AI. And Charles is going to talk to us today about scaling open source LLM models. So please welcome Charles.
Thank you. Hi, everybody. Thank you for joining me for this talk. I am the VP of Engineering at a startup called Together AI. And I'd like to talk today about why we believe open source is the future of LLMs and the future of AI, as well as a couple of things that we found a little surprising as we tried to scale out access to all of these open source large language models. First, a little bit about Together. We are a research-driven AI company trying to bring state-of-the-art research around optimization and building the most efficient infrastructure for large language models and AI in general. We're a young company, but we're actually based off of decades of research done by our founders here, which include professors at Stanford, at ETH, and probably like the best example of our research is flash attention, which was done by Tri Dao over there, and is used by pretty much anybody doing LLMs right now to optimize their training loops. As I mentioned earlier, at Together, we fundamentally believe that open source is the future of AI. We don't think that there's going to be just a single commercial model to rule them all. We think there's going to be a lot of leading models, and a lot of them are going to be open source. And the reason for that is 3 things, really. I think the first is transparency. Anybody who is investing significantly in these large language models is going to want transparency to understand like how the model is behaving. In particular, they're going to want to know what data was the model trained on, what methods were used for training the model, and like how is what is the model quality. And this is important for things like model risk management and model review boards and so forth. And that is partly why we've also partnered really closely with the Stanford Center for Research and Foundation Models to develop Helm. Helm is this benchmark that can benchmark 119 different models across lots of different scenarios and just produce metrics across all these models to see how they actually are behaving and performing. So the second reason we think that the future of LLMs is open source is because of control. So again, if you've invested heavily into these large language models, I think as a lot of us know, these large language models may actually hallucinate issues, and you may put one in production, and all of a sudden it's like hallucinating in production with all of your customers. And so open source models actually give you a lot more control over the behavior of these models. If it's not doing what you want it to do, then you can do a full fine-tune of the open source model. You control when you deploy the model to production and when you want to deploy updates to your customers. And you can actually just download the model and just deploy it anywhere you choose on your own infrastructure or anywhere in the cloud. Like with open source models, like you own the model. And then lastly, like the reason why I believe that open source is kind of the future of large language models is because of privacy. As I mentioned earlier, like you could take the model, you can deploy it on your own infrastructure. You can also use your own infrastructure for training these models and fine-tuning these models. So you can keep control over all the fine-tuning data that you're using, all the input prompts that your model is seeing in production from your users, all the responses from the models, and any other user data that you're using that you feed into the models. So for all these reasons, we believe that open source is actually going to be the future of large language models. And so what we've done at Together is one of the things that we've done is we provided a service where anybody can go to our website, get an API key, and start using any of 100+ open source large language models. We added just like Mixtral support earlier this week, for example. And what I'd like to talk about now is some of the issues that we ran into trying to scale out this service that's serving all of these open source large language models. And I just want to talk about 4 simple things, 4 things that we kind of found surprising to us, at least, as we tried to scale this out. And those are auto scaling and startup, bin packing and robustness, timeouts and keep alives, and continuous batching. So to start with, when we're hosting this many models in production, we want to actually auto scale with our demand. So if we don't want to actually run every single model at peak capacity all the time. And this actually is incredibly challenging. And one thing that is really important to solve when we're auto scaling is model startup. So at Together, we actually have our own inference stack that runs the inference for all of these models. And we spent a lot of time just trying to optimize that stack, optimize that startup time, get it to load the models as quickly as possible, and get ready to serve traffic. And what we found, which was a little bit surprising, is that that actually was not the biggest part of the startup problem. Actually, the startup time was dominated much more by just downloading the models. Because the models actually can be fairly large. A 70 billion parameter model is like 140 gigabytes. And when you have like thousands of GPUs and you have to send all this data to all of the workers and all the services, that actually starts to dominate kind of that startup time. And so one of the things that we had to do there is just to make sure that we were really smart about caching things, caching the models like close to our GPUs, both within the same data center and on each of the instances. And also be really smart about just kind of like predicting where we should pre-cache things. Like if a model is going to be really popular, then just push that model to as many places as you can. So that was a little bit surprising to us. The second thing that actually caught us a little bit by surprise was bin packing versus robustness. So there was this trade-off between robustness and actually being able to auto-scale some of our models. So imagine that you're running a bunch of small 7B models that maybe take 1 or 2 GPUs each. If you want a robust service, then you would spread out those models on as many machines as you can, and each machine may have like 8 GPUs. But then also imagine that you're running a large 70B model that might want all 8 GPUs on a machine. When it comes time to try to scale up that 70B model, it may not be able to find a machine to run on because you've actually spread out all the small models across all the machines, and you can't find a whole machine to run on anymore. So that ended up being really tricky for us as well. We had to set different priorities so that if we try to scale up a 70B model, that we would kick off some of the smaller models and just try to bin pack in order to maintain both robustness and efficiency there. The third thing that kind of caught us by surprise and that we had to actually spend a lot of time on is just timeouts. So one of the things about these large language models is that the requests can take a very long time. End to end, with from the first byte until the last byte of the response, it could be tens of seconds, sometimes like hundreds of seconds, depending on whether you're sending like a huge prompt or not. And this is very different from kind of typical like web traffic or typical internet service. And so what we found is that every single part of the path actually needed some specific tuning on timeouts. In order for us to both make sure that we didn't throw errors with our customers and make sure that we could take best advantage of the persistent connections, the HTTP keep alive connections throughout the entire path. And so the trick there was we had to just map out the entire data path and make sure that the timeouts were getting progressively longer and set progressively longer throughout the whole path. And finally, I want to talk about continuous batching. A lot has been written with continuous batching about how fast continuous batching is in terms of tokens per second and how much it can reduce latency. But what we found was that continuous batching was really essential for us just so that we could handle multiple requests per server. Like without batching in general, like if every GPU could only take one request at a time, there was no way we would have enough capacity to serve all the traffic that we need to serve. And so like continuous batching was just essential just to even just make a scalable service in the first place. So that's those were just a small sampling of the surprises that we ran into trying to scale out the service, and hopefully that maybe helps like you guys avoid some of those if you end up having to scale it yourself. And again, like here at Together, we're providing this service to bring these open source models to the masses because we believe that the future of AI is open source for better transparency, better control, and better privacy. Thank you.
Thank you, Charles. Thank you, Charles. Very good. All right, we're up to our last keynote for the event. Eve Phillips, Director of Product Management at Google, is here to talk to us today. Eve leads the ML Frameworks product team, which includes responsibility for TensorFlow, JAX, and Keras. And she's here today to discuss what's new in AI. So please, welcome. Eve, here you go.
Hi, everyone. It's great to be here. Thank you so much. I'm here to help paint a picture of what you're seeing at this conference and how it ties back to all the incredible innovation that seems to have burst on the scene in the last year in AI/ML. My goal is to help that you think about how all these innovations and related tools that you might use to solve the biggest human needs that inspire you to build these impactful solutions. To truly innovate, we always need to root our innovation back into the problems that we're solving. And so great ML solutions, like any other solution, ideally start with design thinking. Who's your user? What are their needs? And how will solving those needs impact their lives? So right now is an incredibly exciting time for machine learning, whether you're just getting started or a seasoned practitioner. Large model integrations and applications have exploded, from larger companies through to startups. And advancements across the industry range from no low-code offerings to those, as well as those for more advanced practitioners. Now, so many of you are here today because of large language models. So let me walk you through a super short overview. Large models, and specifically large language models through generative AI, have fundamentally changed technology in the last year or so. It's not just the technology, but the ease of access, the natural conversational style of many of the popular applications, and several other underlying factors that have made LLMs seem to have burst onto the scene. Whatever the underlying magic, though, this shift has helped quickly unlock solving big human problems, and in a variety of ways that many of us haven't even figured out yet. And so even if large models, though, don't solve everything, the majority of our critical ML solutions are still running with traditional ML, it's still important to understand that all the underlying advancements that have helped make LMs possible. Because at the end of the day, all this machine learning is inspired by deep human needs. So let me walk through a quick path from the Google side. At first, traditional programming consisted of providing a specific set of instructions for a computer to execute. You had to know precisely which set of actions to follow to get from input to output. So you could teach the computer something in the old days like cat, type, animal, legs 4, ears 2, fur, usually, likes, yarn, catnip, naps, and ultimate power. Well-defined inputs, well-defined outputs. Then neural networks came around in roughly 2012. We started training AIs with a bunch of data, like a pile of animal pictures, teaching the AI which ones were pictures of cats and which were dogs or other animals or just not a cat. After a certain amount of training, the AI became able to figure out which pictures were cats with great quality. The model is a single task model trained to solve a specific problem. But sometimes the outputs could surprise us in good ways, and there was a lot of increased flexibility in the types of inputs we could use. Then this evolved into large language models, or LLMs, which ML algorithms that can help recognize, predict, and generate human languages. LLMs are normally pre-trained for multiple tasks on a large corpus of text, followed by fine-tuning on a specific task, like if you gave a whole encyclopedia to a child and then worked directly with the child to figure out how to do specifically well on questions for cats. And for this training, though, you had to think on terabyte scale, resulting in large models with tens of billions of parameters, which are the weights that the model learned during training and used to predict the next token in the sequence. So now we have a system where we can use really general inputs and get human-like outputs across a wide variety of questions. And so when you take a look behind the scenes of this path, you can see that this large model technology has been gaining momentum for years. And our own path is illustrative to understand where we are now. For the purposes of this chat, I'm going to zoom past a bunch of stuff from Google towards 2017 and the introduction of transformers, an architecture designed around the idea of attention. This architecture made it possible to process longer sequences by focusing on the most important part of the input, solving memory issues that had been encountered in earlier models. Taking us back to everyday life, you can imagine that this state-of-the-art architecture can also be incredibly useful at solving everyday problems like translation. Or AlphaFold, developed by our DeepMind team, which allows access to over 200 million protein structures or predictions to dramatically accelerate scientific research. And several more impactful models started emerging quickly, one after another, powering incredible products here at Google, from T5 to Lambda to Palm to Gemini, our newest model. Now, when thinking about LMs, it's not just thinking about the architecture. There's a number of underlying advancements that I'm going to talk a little bit about across ML software, from computational power to ML techniques to training data to access to innovation, that are all relevant to making this new innovations possible. So first, advancements in computational power. So one of the most important things that you need to understand at a high level is the key infrastructure that ML runs on. Specifically, when you're trying to crunch a very, very large amount of data, you need a whole lot of computing power. Computing resources have become more powerful, such as with GPUs and our own TPUs, first launched in 2015, where you can do a much more complicated processing much faster than in traditional processing units like CPUs. And the key takeaway on this is that it takes a lot of power to run these large models, and even more to train and crunch all the vast amounts of data that are required to get them to a point where they're ready for prime time consumption. And then data. So data is really key to everything. Without data, we know that models simply can't learn. And as we get better at collecting and analyzing large amounts of data, be it structured data or unstructured data like audio or video files, the model performance can improve dramatically. But for you as you develop, figuring out what type of data your customers need or have gets really complicated quickly. Do you need just text to better understand and generate natural written language? What about when it becomes dialogue and spoken conversation? Or we need to communicate with computers through code? Or maybe you need image or audio. Now I want to pause to call out that with more data becomes more responsibility. And it's important to put that responsibility at the core of all product creation that we do in AI. So next, advancements in techniques. So over the last several years, significant advancements in some of these techniques to train the models have also led to some of these large leaps in performance. We covered more power, which means more data crunching, and the ability to handle more diverse types of data. But it's not just about training on more data, but the ability to train faster so that we can have faster feedback loops, meaning the ability to incorporate higher level and higher judgment evaluations of the outputs of the models. Specifically, techniques like reinforcement learning with human feedback, or RLHF, has been critical as models are learning from vast amounts of unstructured data like image, audio, et cetera, which require much higher judgment in knowing how to evaluate the outcomes. Computers in the traditional ML world have only been able to handle simple questions like, is this a hot dog, yes or no? But with faster iterations of humans providing real-time feedback, we can create more nuanced, expert opinions to help guide the models to better judgment, like determining which corgi is the cutest, most dramatic, and corgi-tastic. And with the increased availability of open source models, as we heard from our last speaker, on all sizes of platforms from Kaggle to Hugging Face, et cetera, and open source frameworks like TensorFlow, JAX, Keras, and PyTorch, more and more developers have been able to learn more quickly from each other, innovating faster on the models themselves, the data, the techniques, and the fine-tuning to support a wide variety of use cases solving deep customer needs. This innovation, the overall community expertise, has been critical in supporting the acceleration of innovation around large models. And easier access comes through no-code platforms like LM chat interfaces like Bard or ChatGPT, which dramatically open up access to everyday customers to start using and being inspired by large models without needing to know how to code. It made it as simple as typing whatever you're thinking in whatever language you think in to be able to interact with these LLMs. This has meant that the large models that were previously only available to researchers with deep technical experience and access to large amounts of compute are now available to almost anyone. Because it's been so much easier to access LMs and build with them, we've seen rapid integration of these LMs in applications solving on a diverse set of customer problems across a wide variety of tasks critical to our lives, ranging from assistance to coding to translation, summarization, generation, and more. And this means that the ML running behind the scenes is just that much more approachable for people. Adding to this, a proliferation of smart devices over the last decade has also meant that customers now have devices like phones, wearables, and IoT with them almost all the time, anywhere in the world. This popularity has been, in part, powered by increased advancements in device machine learning, including critical techniques around model optimization and quantization. These capabilities are often baked into the frameworks themselves, whether it's like TF-Lite or MediaPipe, so that developers can meet end users' demands for smarter and smarter applications. On the device that they have them with them all the time, meaning there's greater need for advanced ML capabilities than ever. And with diverse applications and services bring diverse responsibility as you look to build. As we get better at collecting and analyzing large amounts of data, think about how these practical applications can be centered around key human needs. And how can we be responsible? We'll run into a diverse set of opportunities to develop this responsibility, each with their own nuance. And many of the answers to what responsible needs are still being weighed. So it's critical for all of us to keep educating ourselves, staying informed on the latest guidelines, and I know I'm always asking if it's good enough. So what are some of the specific applications out there using AI ML? I'm sure you all know of a whole bunch. I'll give you a few from my day job. We've launched all sorts of products that are powered by LMs, from Bard and Duet AI, which is your AI-powered collaborator across Google Cloud, to help you get more done faster. And this technology also powers a lot of consumer features you probably know and love, like real-time editing features in photos, all the way through to the incredible effects in Meet. And developer products like Vertex AI, Kaggle, Visual Blocks, and Keras 3.0, which is something I'm very excited about, a new rewrite of the Keras APIs that let you run the workflows on either JAX, TensorFlow, or PyTorch, unlocking brand new large-scale model training and deployment capabilities, enabling multi-framework machine learning. We've leaned in to make sure that our ML works great on all your devices so that you have that little bit of magic in your pocket, on your wrists, in your ears, and more. And as of last week, of course, and even more being announced today, Gemini. Gemini is the next phase in our journey around making AI more helpful for everyone. It's the most capable and general model that we've built, and it's the result of a large-scale collaborative effort by teams across Google. And its state-of-the-art capabilities will significantly enhance, we believe, the ways that developers and enterprise customers build and scale with AI across multiple different model sizes. And while I love all ML, I'm particularly passionate about devices, which is why I'm actually really excited for the smallest size model, the Gemini Nano, optimized for mobile, bringing that power of large models with you anywhere, anytime. And the reason this matters is because running on device enables features where the data should not leave the device, such as suggesting replies to messages and encrypted messaging app, and it enables consistent experiences with deterministic latency. So features are always available, even when there's no network. Anyway, bringing it back to you. We're excited about the amazing possibilities of a world responsibly powered by AI, a future of innovation that will enhance creativity, extend knowledge, advance science, and transform the way billions of people live and work throughout the world. And so one parting thought, just don't forget to think about all the cool and core human needs that you're building for and you're building these solutions to address. Whether that's how you might use AI/ML to find a safer path to Mars, or figure out what's for dinner, or just bring a little more fun into your daily life. We're in a great world of possibility where you can make a rainy day a little bit brighter, whether that's literally or figuratively, and I can't wait to see what you all build. Thank you so much.
Oh, thank you, Eve. Thank you. Very good. And a big thank you to all of our speakers this afternoon. I think they did an excellent job, and I think we owe them a round of applause, so thank you. So we are on coffee break now until 2:50. At 2:50, conference sessions will begin. I want to thank all of you for attending this event, and to also keep an eye on your inboxes. You'll hopefully see some information on 2024 events in AI with the Linux Foundation, and hopefully we'll see you all there. And enjoy the rest of the afternoon. Really appreciate it. Thank you.